Hello everyone, my name is Yang and I'm from Inner Mongolia University. Now I'm going to presenting our work, Hierarchical Semantic Alignments for 3D Human Motion Retrieval. Before we introduce the details of our research, let me start by introducing the 3D Human Motion Retrieval. Given a query text, 3D Human Motion Retrieval aims to retrieve semantically relevant motion sequence from a large number of candidate sequences. As shown in the figure, the left side is the query, the right side is the motion sequence related to the query, and the text below each sequence is the annotation of each motion. So the existing work, TMR, mainly follows the cross-modal retrieval, and the query text and the candidate sequence are represented as the global point embedding by text encoder and motion encoder. Then the global similarity is calculated, and then contrastive learning is carried out. As shown in the figure, the matrix is the global similarity matrix, and the SIG denotes the similarity between I's query and J's motion sequence. In recent work, MOT, the answers project the 3D skeleton sequence and text query into a cross-modal common space by a specific motion encoder and text encoder, then performing the single point embedding alignment to achieve text motion cross-modal alignments. So existing work has achieved promising retrieval performance by leveraging the strong global representation learned with the powerful ranking loss and pre-trained encoder. However, relying solely on the global embedding tends to capture only the coarse semantics of motion sequence, struggling to accurately distinguish the intrinsic semantic of complicated motions, especially in case where multiple semantically diverse motion co-occur and superimpose on a single avatar. So the first challenge in this work is how we measure the correlation between the co-occurring motion and the corresponding descriptions. As shown in the figure, the example shows the motion sequence encompasses multiple motions which contain various semantics such as walking and carrying. The motion walking is superimposing on the avatar with carrying, and it is interspersed throughout different sections of the sequence. So the simple approach to extract the global semantic of motion sequence, such as mean pooling, may coarsely capture the overall semantics of sequence, and it is inadequate to accurately model the coupled complex semantics of superimposing motions. And the other challenge is how could we align the subtle motion and the corresponding descriptions. As shown in the example, the motion put things together and stir them occur successively in the sequence, involving only the variation on the head without any change in other body parts. So the single global embedding hardly captures the discriminative semantics of subtle motion, and difficulty enables the local motion alignment. To address the above challenge, we propose a novel hierarchical semantic alignment framework, which incorporates the global representation alignments with fine-grained semantic alignments, aiming to achieve a precise matching between text and motions. Firstly, we adopt two-feature extractor to extract the local-level representation of text and motions. After that, we prepared the three special tokens, class, mu, and sigma, on the local-level features, and feed all of them into the transformer encoder EM and ET. Then we adopt the output of class token as the global representation, and view the output of mu and sigma tokens as the representation of distributions. And the other tokens are the local level representations. So when applying hierarchical semantic alignments, we first align the global embedding of text and motion to match the overall semantics, where the L in 4 indicates the information loss function. We adopt the probabilistic-based distribution alignment to effectively capture the multiple superimposing motion by projecting the text and motion as a multi-dimensional probability embedding. To effectively align the distribution of text and motion, we adopt the Bhattacharya correlation coefficients for measuring the distribution discrepancies and facilitating precise alignments between distributions. In addition, we propose a descriptor-based fine-grained alignment to improve the sensitivity for the subtle motions. In the fine-grained alignment, we introduce feature gating to filter on the representative local feature from word at frame. We adaptively assign word level and frame level repetitions from text and motion into a set of cross-modal local aggregated descriptors, PM and PT, and perform the info-NCE to conduct the fine-grained semantic within the same descriptors. So the fine-grained semantics in word and frame could be interacted. The overall training objectives are combined by the hyperparameter alpha and beta. And to keep the consistency with the training procedure, we adopt the similar alpha and beta to weight the similarity in inference procedure. We evaluate our methods on two widely used benchmark datasets to answer the following question. One, how could HRC compare in performance to the SOTA baseline in text-to-3D human motion retrieval? And what is the impact of each component within HRC on overall retrieval performance? And three, how does the HRC demonstrate generalization across different text-to-3D human motion retrieval backbones? In our experiments, the normal setup adopts all test sets without modification for evaluating the model. The threshold setup search over all test sets and accepts the retrieved motion as correct if the text label is similar to the query text above threshold whose default setting is 0.95. It aims to study the ability of model to this negative pair with significant similarities. In this table, we conduct experiments on human ML 3D. On the normal setup, our HRC outperforms our baseline by a considerable margin. The simple alignment global embedding of text and motion methods such as TMOS and TMR shows an unsatisfying performance. It may be caused by an insufficient semantic capturing of the motions. And directly aligning the cross-global embedding may be difficult to sense the subtle motion, resulting in an unsatisfying performance on the fine-grained retrieval, such as lower performance on the recall S1. On the threshold setup, our proposed HRC still outperforms all baselines, especially the TMR that contains a specific design for negative filtering. Extensive experiments conducted on the KIT-ML benchmark dataset also demonstrate the significant performance achieved by the proposed HRC compared with the SOTA method. In Table 3, we report the results of the evaluation study to verify the effectiveness of components in our method. In the first group, only a single alignment strategy is used to match text and motion. We observe that PDA and DFA shows a better retrieval performance than the global embedding alignment. It indicates that the alignments based solely on global embedding provides limited semantic information to achieve satisfactory retrieval performance. And our proposed PDA and DFA could provide more fine-grained semantic alignments to improve retrieval performance. For the second group of evaluation study, we pair different level alignments to investigate their interrelated effects. We observe that compared with using a single alignment strategy, combining various alignments leads to a notable improvement. And it indicates that the proposed PDA and DFA can provide varying alignments semantic and are complementary to each other. As shown in Table 4, the distillation The distribution indicates the proposed but Chaya distance measurement and the sampling is the Monte Carlo sampling strategy. In compared with Table 4, the introduced approach outperforms the sample strategy by a significant margin, which demonstrates the effectiveness of our method. In Table 5, we aim to verify the generalization of our hierarchical semantic alignments. We plot the proposed HSA into 3 different backbones, TMOS, MOT, and TMR on the dataset Human ML3D. The improvements performance by our HSA are marked in green. All baseline shows a satisfying improvement by equipping with our distribution alignments and fine-grained alignments, which demonstrates the generalization of our method and proves the necessity of the hierarchical semantic alignments in text-to-motion retrieval. In Figure 3, we visualize the retrieval results for text-to-motion retrieval of the proposed HSA and the baseline TMR and MOT. For each method, we showcase the top 2 retrieved results where they are ranked by the similarity and the bottom sentence of each motion sequence are the ground truth test. The successful retrieval results of motion sequence are highlighted by the green border. For the retrieval example, we observe that our proposed HSA successfully retrieved the motions. In Figure 4, we visualize the assignment weight in our descriptor-based fine-grained alignments. We draw each descriptor with distinguished color and give the corresponding assignment weights on the line. The index of frame is below to the image. So in the figure 4, the meaningless words such as and, then are assigned a lower weight to P1, P2, and P3. This is attributed to the proposed fine-grained feature attention, which brings more attention to the significant local representations. It also demonstrates that the DFA can effectively align the word to the corresponding descriptors. In addition, we also show the assigned weight for each frame. For the keyframe of each motion, such as the 2, 6, and 10 frames, the proposed DFA could assign the appropriate weight to the corresponding descriptors. In this paper, we propose a hierarchical semantic alignment framework to model and align the precise semantic for text-to 3D human motion retrieval. We incorporated the global semantic alignment with a probabilistic-based distribution alignment and descriptor-based fine-grained semantic alignment to enable a cross-to-fine semantic alignment between text and motion sequence. The probabilistic-based distribution projects the text and motion sequence as a multi-dimensional probabilistic embedding to effectively capture the semantic of superimposing motions, and the descriptor-based semantic alignments adaptively assign the local representation of text and motion into a set of descriptors with shared semantics and perform interaction between these assigned features to achieve a fine-grained semantic alignment. Comprehensive experiments demonstrate the effectiveness, superiority, and generalization of our method. That's all. Thanks for your listening.